We are now into the final part of the electricity unit. This is basically what it's all been culminating to. We're now going to look at circuits and use Ohm's law to help us figure out various components of the circuit. Before we begin with the math, we need to understand the two basic circuits that we're going to come across: the series circuit and the parallel circuit. The series circuit is a circuit in which there's only one pathway for the electrons to move. A parallel circuit, on the other hand, is multiple pathways for the electrons to move. So what does this look like? Well, a series circuit could look like this. Here's your battery. It goes this way, there's a resistor. This way, there's another resistor. There's another resistor, and so on. It doesn't matter how many resistors. The key thing, though, is to see that there's only one pathway for the electrons to go. It doesn't really have a choice to go any other place else. A parallel circuit, on the other hand, may look something like this. This is just an example. Maybe it goes like this, and goes up, there's a resistor, and goes down and looks like this. But there's also a second wire in there, and there's a junction, and cuts across like this. In this case, since there is a junction here and here, the current actually splits. Current goes not only this way, but it also goes this way as well. So there's multiple pathways, and that's why it's parallel. Now, before we get into the math, we need to know a couple things about each of these types of circuits. Let's first look at series. In a series circuit, you are going to have to calculate what is the total current, and so it'll have the symbol I tot. The total current in the entire circuit is also going to be equal to the current at each individual resistor. So I1 is equal to I2 is equal to I3, and all of those are equal to the total. So for example, if the total current in this particular circuit was, let's say, 10 amps, then that means the current right here is 10 amps, the current right here is 10 amps, and the current right here is 10 amps. And think about it, doesn't that make sense? If charge is entering this resistor, doesn't that charge have to leave that resistor? There's only one pathway, so you can't be losing charge. So you have to have the same current at every single spot. So in series, the current is always the same at every single spot. However, the voltage is not going to be the same. There's going to be voltage drops at every single spot. So the total voltage in the entire circuit is going to be the sum of the individual voltage drops at each spot. So the change in electric potential at spot 1 plus the change in electric potential at spot 2 plus the change in electric potential at spot 3 all have to add up to be the total. So what does that look like? Well, let's say this was connected to a 12-volt battery. Okay? The voltage drop across here, the voltage drop across here, and the voltage drop across here all have to equal 12. So let's make up some numbers. I'm just making things up. Let's say the voltage drop was 2 volts. Let's say the voltage drop here was 5 volts. So how many is that total? 7, right? Well, what would the voltage drop have to be here in order for it to add up to be 12? And that would be 5. So in series, the voltages all have to add up to be whatever the total is. Finally, how do you calculate your total resistance? Your total resistance is just going to be the individual resistors added up together. So the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3 all have to be the total. So let's say, for example, the total resistance in this entire circuit was 15 ohms. If it was 15 ohms, and let's say this one right here was, and I'm making up numbers here, by the way, this is not mathematically correct, we're just looking at just examples here. Let's say the resistor here was 3 ohms. And let's say the resistor here was 6 ohms. Total, that's going to be 9. We know it has to all add up to be 15, which is the total. So we must figure out that the resistor here must be 6 ohms in order for all of that to add up to be 15. Okay, so let's review. The current, the total current, is also equal to the current at each individual spot. The total voltage is going to be equal to the sum of the voltage drops. And the total resistance can be found by adding up the individual resistors. Okay, now let's compare that. Let's verse that to parallel because parallel is different. Okay, for a parallel, the total current in a parallel circuit is equal to the sum of the currents individually. So the current at resistor 1 plus the current at resistor 2. So we see it's opposite of a series. So whatever the current is here plus whatever the current is here needs to equal total what the current is. And think about that. That makes sense because let's say the current right before the junction was 3 amps. When it splits, and it's not going to necessarily split evenly, let's say 2 amps goes up this way. Well, then how much current is going across the branch here? It must be 1 amp. And so the total current in the entire parallel circuit must equal the individual currents added together. On the other hand of that, though, the total voltage is equal to the voltage drop at resistor 1, which is equal to the voltage drop at resistor 2. So for example, let's say this was connected to a 12-volt battery. That means that the voltage here is 12 volts. And that means the voltage here is 12 volts. So we see in parallel, it's the voltage that's the same throughout. Whereas in series, it was the current that was same throughout. Finally, to calculate total resistance, you have to do it in a different way than series. It's going to look weird until we do some examples. 1 over R tot is equal to 1 over R1 plus 1 over R2, etc., for as many resistors as you have in parallel. This looks funky, but we're going to do some examples that will hopefully make sense of this. Okay, let's go slow and do one example for each. Okay, let's look at a series circuit. On the screen, we have set up a very simple series circuit. We can see that it's a series circuit because notice there's only one pathway for the electrons to go. We see that we have 3 resistors. We have a 3 ohm resistor, a 5 ohm resistor, and an 8 ohm resistor, and they're all connected to a 9-volt battery. Okay, I always tell students we need to first figure out what our totals are. So I already know what my V total is because it tells me. It's whatever it's hooked up to the battery. So the V total is 9 volts. Okay, the next easiest one to figure out, let me scroll down here a little bit. All right, the next easy one to figure out is the R total. What's the total resistance? Now, it's a series circuit. Let me move this out of the way. Oops, not that. Wait for it. There we go. I just want to get that out of the way. Okay, it's a series circuit, so remember, the total resistance in a circuit is just the individual resistors added up together. So 3 plus 5 is 8, plus 8 is 16. So the total resistance of the entire circuit is 16 ohms. Now, we know the total voltage, we know the total resistance, so I can find out what my total current is using Ohm's law. So I'm going to do that up here. I tot is equal to V tot over R tot. That's Ohm's law. But notice I'm using the totals. Okay, so the I tot is just going to be the V tot, which is 9 volts, divided by the R tot, which is 16 ohms. If I divide those two together, 9 divided by 16, that's going to give me 0.5625 as my total current. For simplicity's sake, I'm just going to put 0.56. And the current is always measured in amps. Okay, now that we know our totals, now what we can do is we can go in and look specifically at each resistor. What I'm ultimately trying to figure out is I'm trying to figure out what is the voltage and the current at each of these individual resistors here. All right. Remember, what is the same in a series circuit? Is it the voltage or is it the current? If I go back to my notes, notice it's the current. Whatever the total current is also the current at each individual resistor. And so, if my total current is 0.56 amps, it's also going to be 0.56 amps at every single resistor. And so, let's write that up there. I've got 0.56 amps is the amount of current here. 0.56 amps is the amount of current here, and 0.56 amps is the amount of current there. Now look, we have the R for each one of these spots, and we have the I for each one of these spots. All that's left to do is to figure out what the voltage or the potential difference is at each one of these spots. Okay, we're going to find that using Ohm's law again, but this time we're going to use the individual values for those spots. So let's do this first one. Remember, I'm solving for V, and so V is equal to the current times the resistance. For this one right here, the voltage drop for the 3 ohm resistor is going to be the current, which is 0.56, times the resistance, which is 3. 3 times 0.56 is going to give me the voltage drop of 1.68, and my unit is volts. So now I've figured out all the information for my 3 ohm resistor. Let's do this one right here. My voltage is my current is 0.56 times my resistance. This time it's 5 ohms. So the voltage drop across the 5 ohm resistor is going to be 0.56 times 5, or in other words, 2.8. And finally, let's do the same here. My current is 0.56 times my resistance is 8 ohms. And so 0.56 times 8 gives me my voltage drop across the 8 ohm resistor as 4.48 volts. Now let's double check to see if we did this right. Remember, in a series circuit, all the voltages have to add up together to be what my total volt is. And so let's do that. Let's check and see if we did it right. Let's take the voltage drop across the 3 ohm resistor, which was 1.68 volts, plus the voltage drop across the 5 ohm resistor, which was 2.8 volts, plus the voltage drop across the 8 ohm resistor, which was 4.48 volts. And if I add those together, 1.68 plus 2.8 plus 4.48 ends up giving me a voltage of 8.96. That's pretty darn close to 9 volts. The reason why it's not exact is because, remember, we rounded my current. And so our answer is not going to be perfect in the end. If I had used the whole current of 0.5625, it would have come out to exactly 9 volts. So I know that I did it correctly. Okay, now let's do a parallel example. We're going to start out the exact same way we did before. We're going to find out what our totals are. So the first thing I want to write down is, what is my V total? This is usually, like I said, the easiest because it's usually given. The V total is whatever the battery is, and in this case, it's 12 volts again. Or sorry, it's 12 volts. The last one was 9 volts. This one's 12 volts. Okay, what is the resistance? That's usually the next one you find. R tot for parallel is a little bit different, so let me do this off to the side. 1 over R tot is going to be equal to 1 over the first resistor, which is 2, plus 1 over the second resistor, which is 6, plus 1 over the third resistor, which is 10. So what I'm going to first do is I'm going to add my fractions on the right side of the equal sign. So 1 over R tot is equal to 1/2 plus 1/6 plus 1/10 is equal to 0.76666, or if I turn that into a fraction, which you don't have to, but just so you know, that's the same thing as 23 over 30. So 23 over 30 is what I get when I added up these fractions here in my calculator. Now, 23 over 30, which is the same thing as 0.76 repeating, is not what the R total is, it's what the 1 over R total is. So in order to find out what R total is, I need to do the inverse. So let me show you how we do that mathematically. So we have 1 over R tot is equal to 0.76. Okay, so if I take both sides and multiply by R tot, that's going to cancel out the R tot here, and I'm going to end up getting 1 is equal to 0.76 times R tot. Now, to find R tot, all I have to do is divide both sides by 0.76. 0.76 cancel out there, and so my R tot is going to be 1 divided by 0.76 repeating. And that's going to be about 1.3 ohms. Okay, so before I move on, let's review because the parallel is a little bit different. So first of all, you add up your fractions, and then whatever you get on that side, do 1 divided by that answer, and that will give you your R total. Okay, now that we know our V tot and our R tot, we can find our I tot by using Ohm's law. Remember, I tot is going to be equal to V tot over R tot. So I tot is found by taking 12 volts divided by my R tot, which is 1.3 ohms. In other words, 12 divided by 1.3 is equal to about 9.2 amps. Okay, now that we know all of our totals, let's use this information to go in and solve for the individual information at each resistor. Now, remember, what is the same in parallel? Is it voltage or is it current? If we go back to my notes, remember in the parallel, it's the voltage that's the same. And so if we go back here, if 12 volts is my total voltage, it's also going to be the voltage at each of those resistors. So at the 10 ohm resistor, it's 12 volts. At the 6 ohm resistor, it's 12 volts. And at the 2 ohm resistor, it's 12 volts. We can now use this information to figure out what the current is at each of those individual resistors. Okay, remember, current is going to be found by taking your voltage divided by your resistance. So current is found by taking voltage divided by resistance. That's Ohm's law. So let's do it for this first one up here. The voltage, which is 12, divided by the resistance, which is 10, gives me a current of 1.2 amps. For the second one, our voltage divided by my resistance gives me 2. And for my third one, my voltage divided by my resistance, which is 2, gives me 6. And how can you check to make sure it's right? Add up all of these currents. 1.2 plus 2 plus 6 gives me 9.2, which notice was the total current. So that's how I know that I did it right. This concludes the video on series and parallel circuits.